We will discuss how to evaluate indefinite integrals involving products of powers of various trigonometric functions. We will evaluate the indefinite integral of sine x to the nth power times cosine x to the nth power shown on the screen, where m or n is an odd positive integer. First, we assume that the positive integer n is odd. When n equals 1, we evaluate the indefinite integral on line 3. Setting u equals sine x, we have du equals cosine x dx. Thus, by substitution, the indefinite integral on line 3 can be transformed into a simple form, with its result displayed on the last line. When n is greater than 1, we factor cosine x to the nth power into cosine x to the n minus 1th power times cosine x, as shown on line 1. At this point, the positive integer n minus 1 becomes even. Therefore, using cosine x squared equals 1 minus sine x squared, we can rewrite cosine x to the n minus 1th power as a function involving only powers of sine x, as displayed on line 3. Consequently, the original indefinite integral becomes the integral shown on the second to last line, where cosine x to the n minus 1th power times sine x to the nth power turns into a sum of different powers of sine x, all multiplied by cosine x. Next, this integral can be split into multiple indefinite integrals of the form of integer powers of sine x multiplied by cosine x, which matches the integral form on the last line of the previous page. Finally, we can complete the calculation. When m equals 1, we can set u equals cosine x. Therefore, this indefinite integral can be evaluated similarly. When m is greater than 1, we factor sine x to the nth power into sine x to the m minus 1th power times sine x. At this point, the positive integer m minus 1 becomes even. Therefore, using sine x squared equals 1 minus cosine x squared, we can rewrite sine x to the m minus 1th power as a function involving only powers of cosine x. Here, sine x to the m minus 1th power times cosine x to the nth power turns into a sum of different powers of cosine x, all multiplied by sine x. Next, this integral can be split into multiple indefinite integrals of integer powers of cosine x multiplied by sine x, which is exactly the integral form when m equals 1. Finally, we can complete the calculation. In this example, the power of cosine x is odd, so we can apply the rule from the previous page to evaluate this indefinite integral. The first line rewrites cosine x to the 5th power as cosine x to the 4th power multiplied by cosine x. Then, using cosine x squared equals 1 minus sine x squared, we obtain line 2. Next, combining this with sine x squared yields a sum of different powers of sine x, all multiplied by cosine x, as displayed on line 3. We then split this integral into 3 indefinite integrals of integer powers of sine x multiplied by cosine x, shown on the second to last line. These 3 indefinite integrals share the same form, which corresponds to the form previously discussed when n equals 1. Therefore, setting u equals sine x allows us to complete the calculation. In this example, the power of sine x is odd, so we can apply the rule from the previous page to evaluate this indefinite integral. The first line rewrites sine x to the 5th power as sine x to the 4th power multiplied by sine x. Then, using sine x squared equals 1 minus cosine x squared, we obtain line 2. Next, we split it into 3 indefinite integrals of integer powers of cosine x multiplied by sine x, as displayed on the second to last line. These 3 indefinite integrals share the same form, which corresponds to the form previously discussed when m equals 1. Therefore, setting u equals cosine x allows us to complete the calculation. We will evaluate the indefinite integral of sine x to the nth power times cosine x to the nth power shown on the screen, where the positive integers m and n are both even. In this case, we can utilize the trigonometric identities listed on the screen to assist with the calculation. Since cosine x has an even power, using the trigonometric identity listed on the previous page gives us the equality on line 1. Line 2 simply applies the property of linearity to split the integral. Therefore, the indefinite integral on the last line can be easily obtained. Since both sine x and cosine x have even powers, using the trigonometric identities listed on the previous page gives us the equalities on lines 1 and 2. The second to last line simply applies the property of linearity to split the integral. Therefore, the indefinite integral on the last line can be easily obtained. In this example, both sine x and cosine x have even powers. First, splitting sine x to the fourth power into sine x squared times sine x squared yields the equality on line 1. Using the previously listed trigonometric identities gives us the equality on line 2. Then, through simple algebraic manipulation, we split the integral to obtain the equality on line 3. For the first indefinite integral on line 3, applying the earlier trigonometric identity yields the first integral on the second to last line, which can be easily evaluated. Next, we need to compute the second indefinite integral on the second to last line. Since this integral matches the form previously discussed when n equals 1, we set u equals sine 2x, which gives du equals 2 cosine 2x dx. This allows us to evaluate the second integral. After simplifying with algebraic operations, we arrive at the result on the last line. We will discuss how to derive the reduction formulas for sine x to the nth power and cosine x to the nth power individually. We will use integration by parts to prove the reduction formula for sine x to the nth power on line 2. Setting u equals sine x to the n minus 1th power and dv equals sine x dx, we have du equals n minus 1 times sine x to the n minus 2th power times cosine x dx, and v equals negative cosine x. We write the indefinite integral of sine x to the nth power in the form of integral of u dv, as shown on line 1. Expressing the variables u and v back in terms of x gives us the equality on line 2. The last line utilizes the identity cosine x squared equals 1 minus sine x squared. Expanding the mathematical expression on the last line of the previous page yields the expression on line 2. Finally, by treating the indefinite integral of sine x to the nth power as an unknown, we can solve for it to obtain the reduction formula on the last line. This formula shows that the power of sine x is reduced from n to n minus 2. Similarly, we can obtain the reduction formula for the indefinite integral of cosine x to the nth power, as shown on the screen. We will apply the reduction formula to evaluate the indefinite integral of sine x to the fifth power. Substituting into the reduction formula reduces the fifth power to the third power, as shown in the first equality. Applying the reduction formula a second time reduces the third power to the first power, as shown in the second equality. The result on the last line can then be easily obtained. We will discuss the indefinite integrals displayed on line 2. When m equals n, they can be considered as the indefinite integrals shown on the last line. All three of these indefinite integrals are straightforward to compute. Next, we consider the case where m is not equal to n. In this case, we will utilize the trigonometric identities listed on the screen to assist with the calculation. The equality on line 2 directly applies the trigonometric identity from the previous page. Line 3 is simply the result of algebraic manipulation. The indefinite integral on the last line is not difficult to obtain. We will discuss how to obtain the reduction formulas for the indefinite integrals of tangent x to the nth power and cotangent x to the nth power, where n is a positive integer greater than 2. Using the trigonometric identity, we can rewrite tangent x to the nth power as shown on line 3. Then, applying substitution, we set u equals tangent x, which gives du equals secant x squared dx. Therefore, we can evaluate the indefinite integral on the last line. Then, utilizing the mathematical expression on line 3 of the previous 2 pages, we can obtain the reduction formula as shown on the screen. The reduction formula on the previous page was derived for n greater than 2. For n equals 1 and n equals 2, individual calculations are required as shown below. Starting from line 2 is the evaluation of the indefinite integral when n equals 1, which means calculating the indefinite integral of tangent x. First, we rewrite tangent x as sine x divided by cosine x. Then, applying substitution by setting u equals cosine x, we can evaluate it smoothly. The last line shows the indefinite integral of tangent x squared, which is not difficult to obtain by applying the trigonometric identity. Using the previous reduction formula, we can evaluate the indefinite integral of tangent x to the 6th power. We first reduce the 6th power to the 4th power, and then reduce it down to tangent x squared. Since the indefinite integral of tangent x squared was already calculated on the previous page, it is not difficult to obtain the result shown on the screen. We want to obtain the reduction formula for the indefinite integral of cotangent x to the nth power, where n is a positive integer greater than 2. Using the trigonometric identity, we can rewrite cotangent x to the nth power as shown on line 3. Then, by applying substitution, we can similarly obtain the reduction formula as shown on the last line. We will discuss how to evaluate the indefinite integrals of secant x to the nth power and cosecant x to the nth power, where n is a positive integer greater than 2. When n is an odd number, we can use integration by parts to perform the calculation. When n is an even number, we can rewrite secant x to the nth power as the equation shown on line 2, utilizing the identity secant x squared equals 1 plus tangent x squared. Next, setting u equals tangent x gives du equals secant x squared dx. Thus, the indefinite integral of secant x to the nth power can be converted into an indefinite integral of powers of u, which is straightforward to evaluate. Similarly, when considering cosecant x to the nth power, we can rewrite cosecant x to the nth power as the equation shown on the second to last line, utilizing the identity cosecant x squared equals 1 plus cotangent x squared. Next, setting u equals cotangent x gives du equals negative cosecant x squared dx. Thus, the indefinite integral of cosecant x to the nth power can be converted into an indefinite integral of powers of u, which is then easy to compute. Examples will follow to help deepen your understanding. The indefinite integral of secant x squared on line 2 is easy to understand. Next, we evaluate the indefinite integral of secant x on line 4. Setting u equals secant x plus tangent x, we get du equals secant x tangent x plus secant x squared dx. Therefore, applying substitution yields the second to last line. Consequently, the indefinite integral on the last line is straightforward to comprehend. We want to evaluate the indefinite integral of secant x to the 6th power. According to the rule introduced earlier, we factor out secant x squared. as shown in the first equality. Then, utilizing the identity secant x squared equals 1 plus tangent x squared, we convert the remaining part secant x to the fourth power into 1 plus tangent x squared, as shown in the second equality. The third equality converts it into an indefinite integral with respect to the variable u, that is, an indefinite integral of powers of u. Thus, it is easy to obtain its indefinite integral, as displayed on the second to last line. Finally, substituting the variable x back in place of u completes the calculation. We will evaluate the indefinite integral of secant x cubed using integration by parts. We set u equals secant x and dv equals secant x squared dx, which yields du equals secant x tangent x dx and v equals tangent x. The first equality applies the integration by parts formula. The second equality substitutes the variables u and v back in terms of x. The second to last line utilizes the identity secant x squared equals 1 plus tangent x squared. After simplification, we obtain the mathematical expression on the last line. Since the indefinite integral of secant x was previously evaluated, we obtain the mathematical expression on line 2. Finally, by treating the indefinite integral of secant x cubed as the unknown, we can solve for the indefinite integral of secant x cubed on the last line. We will discuss how to derive the reduction formulas for the indefinite integrals of secant x to the nth power and cosecant x to the nth power, where n is a positive integer greater than 2. First, we will prove the reduction formula for secant x to the nth power on the last line. We will apply integration by parts by setting u equals secant x to the n minus 2th power and dv equals secant x squared dx. This yields du equals n minus 2 times secant x to the n minus 2th power times tangent x dx and v equals tangent x. The third line applies the integration by parts formula. The fourth line substitutes the variables u and v back in terms of x. The third to last line utilizes the identity secant x squared equals 1 plus tangent x squared. After simplification, we obtain the mathematical expression on the last line. Next, by treating the indefinite integral of secant x to the nth power as the unknown, we can solve for the reduction formula for secant x to the nth power shown on line 2. Line 4 applies this reduction formula to evaluate the indefinite integral of secant x to the 6th power. We first reduce the 6th power to the 4th power, as displayed on line 4. Then, we reduce the 4th power to the 2nd power, as shown on the second to last line. Since the indefinite integral of secant x squared is tangent x, the calculation is completed and presented on the last line. By the same reasoning, we can also obtain the reduction formula for the indefinite integral of cosecant x to the nth power, as shown on the screen. We will discuss the indefinite integral on line 2. First, assuming n is an even number, we can obtain line 4, in which secant x squared is factored out. Since n minus 2 is also an even number, we can convert secant x to the n minus 2th power into powers of tangent x squared plus 1, as shown on the second to last line. The first equality factors out secant x squared. The second equality converts secant x squared into tangent x squared plus 1. The third equality splits the indefinite integral into two terms, each containing powers of tangent x multiplied by secant x squared. This enables substitution. By setting u equals tangent x, we have du equals secant x squared dx. Then, converting these two indefinite integrals into integrals containing only powers of the variable u makes them easy to evaluate, as displayed on the last line. When m is an odd number, we can factor out secant x tangent x, as shown on line 2. At this point, m minus 1 is an even number, so we can convert tangent x to the m minus 1th power into powers of secant x squared minus 1, as shown on the second to last line. The first equality factors out secant x tangent x. The second equality converts tangent x to the 4th power into secant x squared minus 1 squared. The third equality splits the integral into 3 terms, each involving powers of secant x multiplied by secant x tangent x. This allows substitution. By setting u equals secant x, we obtain du equals secant x tangent x dx, converting these 3 indefinite integrals into integrals containing only powers of the variable u makes them easy to evaluate, as displayed on the last line. When m is an even number, we can utilize the identity tangent x squared equals secant x squared minus 1 to convert the integrand tangent x to the mth power times secant x to the nth power into a sum of powers containing only secant x. At this point, we can apply the previously discussed reduction formula for the indefinite integral of secant x to the nth power to evaluate the integral of each term involving powers of secant x. According to the rule, by utilizing the identity tangent x squared equals secant x squared minus 1, we convert the integrand tangent x squared times secant x into a sum of powers containing only secant x, as shown on line 1. Then, we split it into 2 indefinite integrals involving powers of secant x, as shown on line 2. Finally, by applying the previously evaluated indefinite integrals of powers of secant x and simplifying through algebraic operations, we obtain the mathematical expression on the last line.